Hello dear learners, hope you have seen the first part of the chapter and understood it well. We are going to move further in this session and study about electric field lines, electric dipole and field due to the dipole. We will also discuss other topics like dipole and its fields, etc. The physics of Coulomb's law tells us how to find the electric force on a particle 1 of charge q1 when the particle is placed near a particle 2 of charge q2. A question still remains. How does particle 1 know that there is another particle 2 present? That is, since the particles do not touch, how can particle 2 push on particle 1? How can there be such an action at a distance? So, let us try to find the answer to this question. We will now first see what will be the takeaway for our students from today's session. Students will be able to understand the concept of electric field and properties of electric field lines. Then, how to calculate electric field at the eggshell line and in the equatorial plane of electric dipole. So, now let us first start with electric field. Let us consider a point charge q placed in vacuum at origin O. If we place another charge q at point P such that OP is equals to R, then the charge q will exert a force on small q as per Coulomb's law. We may ask the question, if charge q is removed, then what is left in the surrounding? Is there nothing? If there is nothing at point P, then how does a force act when we place the charge q at this point P? In order to answer such questions, the early scientists introduced the concept of field. According to this, we say that the charge capital Q produces an electric field everywhere in the surrounding. When another charge small q is brought at some point P, the field then acts on it and produces a force. The electric field produced by the charge capital Q at point R is given as ER is equals to 1 by 4 pi epsilon naught Q upon R square and R cap, where R cap is the vector upon the magnitude of this R. It is a unit vector and it is from origin to the point R. Thus, equation specifies the value of electric field for each value of the position vector R. The word field signifies how some distributed quantity, which could be a scalar or a vector, varies with the position. So, learners, can you find out the force acting on q due to small q? Yes, the force on this charge will be F is equals to 1 by 4 pi epsilon naught product of the charges q upon R square into R cap. Now, tell me, will the charge q also exert force? Yes, this charge small q also exerts an equal and opposite force on the charge capital Q. The electrostatic force between the charges q and q can be looked upon as an interaction between the charge small q and the electric field of q and vice versa. If we denote the position of charge small q by the vector r, it experiences a force F equal to q multiplied by the electric field E at the location of charge small q. So, Fr will be equal to q into E at that position r. Can you find out the SI unit of electric field from this equation? Yes, it will be Newton per coulomb. So, you now think of the name we give to charges capital Q and small q. Let's see that in the next slide. The charge capital Q which is producing the electric field is the source charge, and the charge small q which is called as the test charge. But will there be electric field even when there is no test charge? Yes, the field due to Q is independent of the presence of the test charge small q. Now we are in a position to define the electric field formally. So, electric field is defined as limit Q tends to 0 force upon the test charge. If Q is unity, then the electric field due to capital Q will be numerically equal to the force exerted by it. Thus, electric field due to a charge capital Q at a point in the space may be defined as the force that is a unit positive charge would experience if placed at that point, and the force F is then negligibly small, but the ratio F by Q is finite and defines the electric field. Now the question arises, is it practically possible to keep capital Q undisturbed even in the presence of this small charge q? A practical way to get around the problem is to hold capital Q to its location by some unspecified forces. This may look strange, but actually this is what happens in practice. Now the next thought that is coming to our mind is, does E depend on small q? Well, yes, that the electric field E due to capital Q, though defined operationally in terms of the small test charge q, is independent of this charge. This is because F is proportional to Q. So, the ratio F by Q does not depend on small q. Well, the direction of force is directed away from the point charge if capital Q is positive, and directed towards the point charge if that is negative. The direction of force is directed away from the point charge if capital Q is positive, and directed towards the point charge if Q is negative. The direction of E, that is electric field, is same as that of the force on the positive test charge. Directed away from the point charge if Q is positive and towards if Q is negative. Now let's try to extend this concept and calculate electric field due to multiple charges as we did for electrostatic force also. Consider a system of charges, that is Q1, Q2, Q3, Q4 and up to Qn, with position vectors R1p, R2p, R3p and R4p and so on, relative to some origin O. Like the electric field at a point in space due to a single charge, electric field at a point in space due to the system of charges is defined to be the force experienced by a unit positive test charge placed at that point, without disturbing the original positions of the charges Q1, Q2, Q3 and Q4 up to Qn. We can use the Coulomb's law and the superposition principle to determine this field at this point P, denoted by the position vector R. Now, the electric field E1 at R due to Q1 at R1 will be given by E is equals to 1 by 4 pi epsilon naught charge, that is Q1, divided by the position vector, that is R1p square, and unit vector R1p. Similarly, the second electric field, that is field due to Q2, will be 1 by 4 pi epsilon naught Q2 upon R2p square multiplied by the unit vector R2p, where R2p is again a unit vector in the direction from Q2 to P. Similar expressions hold good for the electric field E3, E4 and En due to charges Q3, Q4 up to Qn. Now find the total electric field at the given position. We use the superposition principle. Let's see that further. In the superposition principle, the electric field at R due to system of charges will be E1 vector plus E2 vector plus E3 and so on up to En vector, which is equal to 1 by 4 pi epsilon naught Q1 upon R1p square and multiplied by the unit vector plus E2, which will be 1 by 4 pi epsilon naught Q2 upon R2p square and unit vector R2p plus up to so on 1 by 4 pi epsilon naught Qn divided by Rnp square and then multiplied by the unit vector. So, in this way we can calculate electric field due to any number of charges. Well, now you may wonder as to why this concept of field has been introduced. Let's try to understand this in the next slide. Well, after all, for any system of charges, the measurable quantity is the force on a charge, which can be directly determined using Coulomb's law and the superposition principle. Why then introduce this intermediate quantity called the electric field? Well, for electrostatics, the concept of electric field is convenient but not really necessary. Electric field is an elegant way of characterizing the electrical environment of a system of charges. Electric field is the characteristic of the system of charges and is independent of the test charge that you place at a point to determine the field. The term field in physics generally refers to a quantity that is defined at every point in the space and may vary from point to point. The true physical significance of the concept of electric field, however, emerges only when we go beyond electrostatics and deal with time-dependent electromagnetic phenomenon. Do you know who first introduced the concept of electric field? Yes, the concept of electric field was first introduced by Faraday and is now among the central concepts in physics. Michael Faraday, who introduced the concept of electric fields in the 19th century, thought of the space around a charge body as filled with lines of force. Although we no longer attach much reality to these lines, now usually called electric field lines, they still provide a nice way to visualize patterns in the electric field. Let us represent E due to a point charge pictorially. As we know, electric field is a vector quantity, so it can be represented as we represent the vectors. But how to draw these vectors? Let's find out. Let the point charge Q be placed at origin. We draw small vectors pointing along the direction of the electric field with the lengths proportional to the strength of field at every point. Since the magnitude of electric field at a point decreases inversely as the square of the distance of that point from the charge, the vector goes shorter and shorter, as you can see in this diagram. One goes from the origin, always pointing radially outwards. In this figure, each arrow indicates the electric field, that is, force acting on a unit positive charge placed at the tail of that vector. Then we connect the arrows pointing in one direction and resulting figure represents a field line. We thus get many field lines all pointing outwards from the point charge. But have we lost the information about the strength or magnitude of the field now? Because it was contained in the length of the arrow. No, we haven't. But why not? Because now the magnitude of the field is represented by the density of the field lines. E is strong near the charge, so the density of field lines is more near the charges and the lines are closer. Away from the charge, the field lines get weaker and the density of the field lines is less, as you can see, and it results in a well separated lines. But the number of field lines drawn may vary from person to person. Another person may draw more lines, but the number of lines here is not important. In fact, an infinite number of lines can be drawn in any region. It is relative density of the lines in different regions which is important. We will understand this by saying, having drawn a certain set of field lines, the relative density, that is closeness of the field lines at different points, indicates the relative strength of electric field at those points. The field lines crowd where the field is strong and are spaced apart where it is weak. We can imagine two equal and small elements of area placed at point R and at point S. The number of field lines in our picture cutting the area elements is proportional to the magnitude of field at these points. The picture shows that field at R is stronger than the field at S. The picture of field lines was invented by Faraday to develop an intuitive non-mathematical way of visualizing electric fields around the charged configurations. Let's now look at the field lines due to some given charges configuration. We will first start with a positive charge. An electric field line in general is a curve drawn in such a way that the tangent to it at each point is in the direction of net field at that point. An arrow on the curve is obviously necessary to specify the direction of electric field from the two possible directions indicated by a tangent to the curve. A field line is a space curve, that is curve in 3 dimensions. So, on the screen, field lines due to a positive charge is seen. The field lines are in 3 dimensions, though the figure shows them only in a plane. The field lines of a single negative charge are radially inwards as seen on the screen. The field lines around a system of 2 positive charges Q and Q give a vivid pictorial description of their mutual repulsion. The configuration of 2 equal and opposite negative charges, that is a dipole, show clearly the mutual attraction between the charges. Let us now discuss few important properties of electric field lines. The electric field lines always start from positive charges and end at negative charges. If there is a single charge, they may start or end at infinity. In a charge-free region, electric field lines can be taken to be continuous curves without any breaks. Now, the next property is 2 field lines can never cross each other. But why not? Well, if they did, the field at the point of intersection will not have a unique direction, which is not possible. Fourth, that is electric field lines do not form any closed loop. This follows from the conservative nature of electric field. Let's now check our understanding with the help of a numerical problem. The question is 2 point charges QA 3 microcoulomb and QB minus 3 microcoulomb are located 20 centimeter apart in vacuum. What is the electric field at the midpoint O of the line AB joining the 2 charges? And if a negative test charge of magnitude 1.5 10 to the power minus 9 coulomb is placed at this point, what is the force experienced by the test charge? Let's try to find out the answer to these questions. So, we have 3 microcoulomb and minus 3 microcoulomb kept at point A and at point B. They are placed 20 centimeter apart. So, this distance AB is 20 centimeter. We have to find out the electric field at the midpoint. So, midpoint means, let us say that point is O, this will be 10 centimeter and this charge is also 10 centimeter. Electric field at O will be due to 3 microcoulomb as well as due to minus 3 microcoulomb. So, electric field at O, that is the midpoint, is equal to electric field due to charge at A plus electric field due to charge at B. Now, can the learners identify the direction in which electric field is acting due to both the charges? Well, for that we need to consider a positive test charge at the midpoint O. Due to this, we have the electric field at this point. This will be due to the positive charge, as this charge will repel the test charge and this minus 3 microcoulomb will attract it. So, this direction will again be same and this will be E due to B. So, since both of them are acting in the same direction, so we are adding these two electric fields. So, learners, you know what is the field due to a point charge? This will be 1 by 4 pi epsilon naught QA divided by 10 centimeter, and to convert we divide by 100, plus this electric field due to B will be same 1 by 4 pi epsilon naught Q at B, again 10 centimeter. So, this will be conversion 10 by 100 square, and the net electric field is also towards point B. So, the learners can find out the value of this electric field. After finding out the electric field, it becomes easy to evaluate the force. So, in the second part, the force will simply be the charge into the electric field at point O. Charge Q is already known to us, which is minus 1.5 10 to the power minus 9 coulomb, and electric field will be calculated from this expression. In this way, they can find out the total force acting at point O. Let us now discuss the next topic, that is electric flux. In the picture of electric field lines described above, we saw that number of field lines crossing a unit area placed normal to the field at a point is the measure of the strength of the electric field at that point. This means that if we place a small planar element of area delta S normal to E at a point, then the number of field lines crossing it will be proportional to E into delta S. Now, suppose we tilt the element by an angle theta, clearly the number of field lines crossing the area element will be smaller. The projection of the area element normal to E is delta S into cos theta. Thus, the number of field lines crossing the delta S will be proportional to E into delta S into cos theta. But when this theta becomes 90 degree and field lines will be parallel to delta S and it will not cross at all. This shows that the area element should be treated as a vector. It has a magnitude and also a direction. But how to specify the direction of a planar area? Clearly, the normal of the plane specifies the orientation of the plane. Thus, the direction of the planar area vector is along its normal. How to associate a vector to the area of a curved surface? We imagine dividing the surface into large number of very small area elements, and each small area element may be treated as a planar and a vector associated with it. We notice an ambiguity here. The direction of an area element is along its normal, but a normal can point in two directions. Which direction do we choose as the direction of the vector associated with the area element? This problem is resolved by some convention appropriate to the given context. For the case of a closed surface, this convention is very simple. And what's that? Let's see that in the next slide. The vector associated with every area element of a closed surface is taken to be in the direction of the outward normal. This is the convention used in this figure. Thus, the area element vector delta S at a point on the closed surface equals delta S n cap, where delta S is the magnitude of the area element and this n cap is the unit vector in the direction of the outward normal at that point. We now come to the definition of electric flux. Electric flux delta phi is equal to E into delta S, and it is the dot product, is equal to E delta S cos theta. Here flux is proportional to the number of field lines cutting the area element, and the angle theta here is the angle between E and delta S. The basic definition of electric flux can be used in principle to calculate the total flux through any given surface. All we have to do is divide the surface into small area elements, calculate flux at each element and add them up. Thus, the total flux through the surface S is approximately equal to the summation of E dot delta S at that point. After discussing flux, let's now discuss about a new quantity, and it is called as an electric dipole. Let's see what it signifies. Well, an electric dipole is a pair of two equal and opposite point charges plus q and minus q separated by a distance 2a. The line connecting the two charges defines the direction in the space, and by convention, the direction from minus q to plus q is said to be the direction of the dipole. The midpoint of locations of minus q and plus q is called the center of the dipole. Can you tell what is the total charge of the dipole? Yes, that's correct. It is 0. But does that mean the electric field is also 0? Well, the answer is no. No, the field line of the electric dipole is not 0. Let us see the terms related to the electric dipole in the next slide. First is the electric dipole moment. It is defined as the product of either of the charge, that is plus q or minus q, and the distance between the two charges. Now, this p cap is the direction of the dipole moment. From this equation, we have very important inferences, and they are that the magnitude of the dipole moment is q into 2a. The direction of the electric dipole moment is from minus q to plus q. And dear learners, can you tell the unit of dipole moment? Yes, it is coulomb into meter. So, in the figure, now here you can see a dipole with two equal and opposite charges. The electric field of both the charges is to be calculated. The electric field of the pair of charges minus q and plus q at any point in space can be found out by using Coulomb's law and the superposition principle. We have to now calculate the electric field due to this arrangement at the given point P. Here, the field due to this negative charge will be 1 by 4 pi epsilon naught q upon distance which will be r plus a whole square p cap. E, that is electric field due to positive charge, this will be 1 by 4 pi epsilon naught q upon this distance, which will be r minus a whole square p cap. Now, what will be the net electric field? The net electric field will be E due to minus q and E due to plus q. This is due to minus q and in this direction due to plus q. Now, solving this equation, after putting the values of electric field, we get 1 by 4 pi epsilon naught q, 1 upon r minus a whole square, this minus as it is 1 upon r plus a whole square and p cap. After solving, we get 1 upon 4 pi epsilon naught q, 4 ar upon r square minus a square whole square and p cap. If this distance r is much larger as compared to distance between the charges, then it will be 1 by 4 pi epsilon naught 2, we can write this 4 as 2 into 2 a and r cube p cap. So, net electric field will be 1 by 4 pi epsilon naught 2p, because p is q into 2a p cap 1 r into raised to the power 3. So, we finally get the electric field due to this electric dipole in terms of the dipole moment P. Can you tell what will be the direction of net electric field at this point P? Yes, it will be in the same direction as P, where P is the dipole moment and it is from minus q to plus q. So, electric field will also be towards left. Now, let us calculate the net electric field due to a dipole on the equatorial plane. Again, by the same concept, we first write electric field due to the positive charge at this point P, which will be given by E is equal to 1 by 4 pi epsilon naught q under root r square plus a square ka whole square, which will be r square plus a square, and electric field due to this negative charge will be 1 by 4 pi epsilon naught q upon under root of r square plus a square whole square, that will be r square plus a square simply. Now, solving this equation, we get that the sign components gets cancelled, and can you think of a reason why there is this negative sign? Yes, it is there because the electric field is opposite to the electric dipole moment P. Putting the values of the electric field due to positive charge and due to negative charge, we get 2qa upon this 4 pi epsilon naught r square plus a square raised to the power 3 by 2 p cap. Again, if we consider that distance is much larger as compared to distance between the charges, then it will be 2qa upon 4 pi epsilon naught r raised to the power 3. This negative sign indicates, as we discussed now, that this is due to the fact that dipole moment and the electric field are in the opposite direction. Now, the magnitude of the electric field will be 1 by 4 pi epsilon naught p upon r cube, where p is the dipole moment, which is k p by r cube, and here k represents 1 by 4 pi epsilon naught. If we write that in the vector form, it will be vector E, that is electric field, is equal to minus k p vector divided by r cube, and this reason for negative sign is already known to us. What about epsilon naught? Epsilon naught is the permittivity due to the free space. So, now we have the final expression of electric field in terms of the electric dipole moment as is given by this expression. Now, can you tell me what is the direction of P? Yes, we have already discussed that the direction of P vector is from minus q to plus q as is given in the figure also. With this, we come to the end of this session. So, what all did we learn today? We studied about the concept of electric field, field due to a point charge and a system of charges. Then we learnt about electric field lines and pattern of field lines due to a number of different arrangement of charges. Then we moved on to electric dipole. What is a dipole? Yes, it is a system of equal and opposite charges separated by some distance. We also calculated electric field due to a dipole on axial line and equatorial plane. Dear learners, do you know sprites form an electric dipole? But what these sprites are? Sprites are basically huge flashes that occur far above the sky and during the large thunderstorm. They were seen for decades by the pilots flying at night, but they were so brief and dim that most pilots assumed that they were just illusions. Then later, in the 1990s, sprites were captured on a video. They are still not well understood but are believed to be produced when specially powerful lightning occurs between the ground and the storm clouds, particularly when the lightning transfers a huge amount of negative charge minus q from the ground to the base of the clouds. We can model the electric field due to the charges in the clouds and the ground by assuming a vertical electric dipole that has charge minus q at cloud height h and plus q at below the ground depth h. With this, I conclude my session. We will meet in the next session. Till then, happy learnings. Thank you.